Now we're ready for Chapter 5, Amateur Radio Equipment. When you read the chapter, they took you through some information on modulation, on how you combine information with RF radio signals so you can transmit them. Went over some basic operation of transmitters, receivers, and amplifiers. Hold on a second, I got to make sure I've got my lightsaber going here. Yep, there it is. Okay. Basic operation of transmitters, receivers, and amplifiers. Got into digital mode characteristics. That's kind of a fun, neat section of ham radio that you may not be aware you can do. And then get into power supplies and batteries a little bit. So those are all both necessary for operating amateur radios. So we'll get started. Want to get back to the beginning, which in this case is a voice communication that we want to make. And generally speaking, human hearing's in the 20 hertz to 20 kilohertz range, but generally it's far more sensitive to the 1 kilohertz to 4 kilohertz range, and that's where a lot of the audio is, the bandwidth in amateur radio. So what we're doing is, if you get down to basics, we're speaking, and then the air compression impacts the microphone that converts that sound energy to an electrical signal. And if you were to look at the sound signal on a fast recorder or an oscilloscope, you're going to see the amplitude of the sound signal change as your voice changes. And what we need to do is figure out how to get this audio signal in a condition that we can transmit it on a reasonably sized antenna. If you go through the calculations of the antenna design necessary to transmit a signal in the 1 kilohertz to 4 kilohertz range, you're looking at several miles long antenna, which just isn't practical. So we've got to be a little clever here and do some of that electrical operation. So what we do is we need to take the voice signal and impose it on a carrier signal that is a higher frequency, a radio frequency. And there are a variety of ways of doing that. One way is what's called amplitude modulation, where an oscillator generates a constant magnitude sine wave, and then the envelope of the sine wave is modified so that it replicates the audio signal that you're wanting to transmit. So what we'll be doing then is we're going to transmit a signal whose amplitude changes as the input signal changes. Another technique that's used called frequency modulation, you probably know this as FM on your car radio. And the way that works is that rather than changing the amplitude of the carrier, we change the frequency to be to represent the audio signal. So you can see here an oscillator generates a sine wave, and as the audio signal changes, it changes the frequency of the oh, I'm saying that wrong. It's not this. This isn't audio. This is digital, where we're transmitting ones and zeros. So if we're wanting to represent a 0, we adjust the frequency of the oscillator to this frequency, and then to go to a 1, then we go to a higher frequency, so that the receiver would see this as 0, 1, 0, 1. And you can see the frequencies change to indicate the change from the binary 0 to a 1 and then 1 to 0. And then there's another technique called phase modulation, where we generate the sine wave, and rather than changing the frequency, we change the phase. Now, it's kind of hard to see, but if you look at this sine wave here, we're going up and down, we come down, back up, and if we weren't changing the state, going from a 1 to a 0, then we would continue on up. But what we do instead at that point where the signal needs to become a 1, we reverse the phase. So instead of going up, it starts going down, and then the frequency continues until it needs to change the state again. And you can see right here that it goes up, comes down, and then goes back up rather than going down. And that indicates the start of the higher binary state, or the 1. So there are a lot of different ways to modulate information on a carrier. These are just 3 of them, and probably the most common. So we'll kind of zoom in on this a little bit, and we'll take a look at amplitude modulation. This is the way that the AM stations, the commercial stations, operate. And they'll take the signal that we want to transmit. It could be voice, it could be music, whatever, and combine it with the carrier signal. And the frequency of this carrier signal is what you dial your radio tuner to. So like here, we have an AM radio station, commercial station 1420. So that would be 1.420 kilohertz, I believe. And so that's your carrier frequency. And then what's actually transmitted is the modulated frequency, that is that carrier frequency with the amplitude adjusted by the information signal we want to transmit. Another way of doing modulation is if you're operating CW, or continuous wave, Morse code, the key turns the oscillator on to the amplifier, and the length of the time it's on determines whether it's a DIT or a DA. So you can see here, this is a DIT, this is a DA. And then you could also do this is an AM modulation here, where there's an audio tone that modulates the carrier. Then this is another look at FM, or frequency modulation. We have our base frequency. We want to transmit this modulating sine wave, and you can see here that as the signal increases, the frequency increases or decreases. And then as the frequency or the signal goes negative, below the average, then the frequency gets higher. So by changing this frequency, we're sending the information of the sine wave as changing frequency in the signal. And then on digital modulation, several different ways to do that. One is referred to as ASK, or Amplitude Shift Keying. And here you can see it's pretty obvious that if this is a signal you're wanting to send, a digital signal between 0 and 1, when it's a 0, we have a small amplitude signal. And then when we want to transmit a 1, then the amplitude of that carrier wave is larger. And then we go back to a lower amplitude carrier when we want to transmit the 0, and then back up to a higher amplitude when we're transmitting a 1. So this is how you can send 1s and 0s digitally through a radio. The third one is called on-off keying, or OOK. And what this is, it's a variation of the ASK in that rather than having a low level carrier for 0, there's no signal. And then the signals that is only transmitted when there needs to be a 1. And one of the advantages of this is that it cuts your power consumption a little bit because you're not transmitting when the desired signal is a 0. And then this is a look at the frequency shift keying. You have to kind of zoom in there to see it, but you can see that the frequency changes. The frequency stays the same, but the phase changes, and instead of going up, it'll go down. So this transition here says this is the start of a 1, and it'll stay a 1 until you get the phase shift again, indicating a 0. Nope, I said that wrong. That's not phase shift keying. That's frequency shift keying. The frequency changes between two frequencies to indicate a 0 and 1. So this lower frequency is a 0 up here. Then higher frequency indicates a 1, 0, and 1. So sorry about that. Get to look into these things, they all start looking the same. Now the other thing that's interesting is that what we've looked at so far is the signal in what's called the time domain, where this is increasing time as time goes on, and then the signal changes in time. We're also interested in seeing what the resulting frequencies are from this audio signal and the carrier. And there's a technique, a mathematical technique that can be used to convert the time domain to a frequency domain to where on this AM signal, the horizontal axis is time, and then the conversion changes the horizontal axis to frequency. And what we end up with is a signature for this signal in the frequency domain that looks like this, where in this case, the carrier frequency is 500 hertz. And the information is carried in what's called a sideband. And there are two sidebands. There's a lower sideband. This particular sideband is 100 hertz below that. And then there's an upper sideband. And this is where the variation in the signal's carried. So that when the signal gets to the receiver, what the receiver will do will be to extract, if it's an AM signal, it'll extract and combine both sidebands and reproduce the audio signal that we're trying to transmit. So looking at that same type of representation of the signal in the frequency domain, just wanted to identify the parts of the signal. And you have the AM bandwidth. This would be the total frequency range that the signal would require. And in amateur radio, typically an AM bandwidth is about 6 kilohertz from here on the lower sideband to the upper sideband. The lower sideband has a bandwidth which is half of the AM bandwidth, and the upper sideband takes up half of the bandwidth. So these are about 3 kilohertz wide. And then the carrier signal is right there. That's the magnitude of the carrier signal. And what generally happens if you're operating an amateur radio rig on HF, or you could do it even on VHF and UHF, is if you're operating AM, then you usually transmit just one of these sidebands, because to transmit both of them requires more bandwidth, which takes up the frequency spectrum, and the information in the upper sideband is the same as the lower sideband. So you just suppress the carrier, and depending on what band you're on, then you either transmit the lower sideband or the upper sideband, and you're using about 3 kilohertz of bandwidth to do that. So now we're going to take a look at transmitters, receivers, and transceivers, and just had some pictures here to kind of show you some typical shacks. Well, I wouldn't say these are typical. This one is an older, obviously an older vintage of equipment. This one's older vintage equipment. This one's a little more current. But a couple things to note on this. I mean, these look pretty involved, but the thing you need to keep in mind is that a shack like this one is usually developed over years and years and years of operating, where the ham will buy new equipment and add it to his shack, and then over the years, and you can kind of see that here. You're probably not too familiar with the vintage equipment, but you can kind of see a technical progression here to where some of these are newer radios than this one, and then kind of a common thing in the modern day ham shack is to tie computers to your radios to help you operate it, give you a lot of capabilities to do things. So to start talking about the transceivers, we want to take a look back at the band plan. And the thing, there's kind of a delineation mark, I guess you would call it. Your technician license is going to give you privileges on this band plan. You can see the T, that's for technician. That shows you the frequencies that you'll be able to operate when you get your license. And generally, the technician license is from a part of 10 meters through 6 meters. You can see on 6 meters, you can operate the whole band like everybody else. 2 meters, and then on 1.25, 70 centimeters, the technician has full privileges on that band, as well as 33 and 23 centimeters. Now, when we started, I forget if it was chapter 1 or 2, we talked about the fact that probably the most of your time as a technician, you'll focus on 2 meters and 70 centimeters. And 2 meters is considered a VHF, or very high frequency band, and 70 centimeters is considered an ultra high frequency band. So what that means with your technician license, you're probably going to be focused primarily on VHF and UHF transceivers. Everything above 10 meters and above is considered HF, and these are the bands that are reserved for general, advanced, or extra licensees. So that's kind of the same delineation on the radios. They kind of have a 2 meter, 70 centimeter type of transceivers, and then you have radios that are designed to operate on these bands, which are called HF transceivers for high frequency. So this is the high frequency range, very high frequency range, and then the ultra high frequency range here. So that hopefully gets you kind of reoriented in it to the band plan and where you're going to be able to operate. And then once you get your general license, then that's going to open up all these bands to you. You'll have privileges on each one of those bands to operate, and that's when you'll be looking at an HF transceiver. So this is just kind of a summary of the band plans. You can see here 10 to 160 meters. That goes from 1.8 megahertz to 28 megahertz. This is the HF, and actually the 160 meters is considered MF for medium frequency. VHF is the 6 meters, 2 meters, 1.25 meters, and then UHF is the 70, 33, 23, and 13 centimeter bands. And these are the ones we'll be talking about when we're looking at VHF, UHF transceivers. These are the frequency bands that we'll be looking at when we're talking about the HF, or high frequency transceivers. Now, to kind of give you an idea of the transceiver market, I put this table together, and I need to make a disclaimer. This is just my opinion. It's not an exhaustive listing of all the different types of radios and suppliers that are around, but I think this will give you a feel for the transceiver market on what equipment's available and what the approximate price range is going to be. So let's start off at the bottom here with used equipment. And there are many brands of used equipment. Ham radio's been around for well over 100 years. There have been a lot of companies come and go. There's a lot of used equipment on the market, and it can be a good source for getting your initial transceivers. And generally, you could probably find used equipment, this is the HF transceiver column, in the $100 range on up from there. And then for the VHF, UHF, this would be a little walkie-talkie handheld. We call those HTs. You could probably pick one up from somebody for $10. And then getting into the new equipment, the imports are probably the lowest cost available. There are many brands of imports coming into the country. They all need to be FCC approved. And generally speaking, for an HF transceiver from an import, I've seen a couple of them that have been touted as being fairly capable for about $600, and they go up from there. And you can get a VHF, UHF handheld new. There are companies like Bofang is probably the most prominent one in the foreign handheld market, and you can get your basic handheld VHF, UHF transceiver for about $30. And then they have models for all of these, both on HF and VHF, UHF, that go up in capability along with the price going up. So this is kind of the entry point for the imports. And then if you go to what I would consider entry level, this would be something you would consider after you complete your general license. There are 4 main brands that I've seen that have entry-level HF transceivers, and they're all, I think a Linco might be a little bit below $1,000, but the way prices are going these days, you never know. But generally speaking, for a brand new entry-level name brand transceiver, you're probably going to start at about $1,000. Now, I will say one thing, and again, this is just my opinion. I don't think you can make a mistake in selecting the entry brand radio from any of these suppliers. I think every one of them will do a good job for you. So what will be the determining factor for you will be money, because there's a little bit of difference in price amongst these entry-level radios, but also the capability of the radio, the functions that it has, the features. They're all pretty similar in that respect, but they do differentiate themselves a little bit, and that's where the studying comes in, particularly when you're studying for your general. It's just not for you to pass the test, but you'll pick up the knowledge you need to make that decision of whether you'd want this brand or this brand or this brand or this brand. And you can also get the help of some your ham buddies. You'll probably find people that have uh, entry-level radios from all these suppliers, and give you a chance to talk to them and get to operate it after you get your license. Um, like I said, the HF radios in this range start around $1,000, maybe a little lower. And then the Vhf UHF handhelds and base units start at about 150 and go up from there. And then there's another upper tier, what I call, this is my terminology, an upper tier level, and that is not the entry level radio. This would be the kind of radio you would consider buying after you've had some good experience at operating on HF, and you become comfortable with what you need and know what you're going to want to be able to do with an improvement in your radio. And then these three companies have what I would consider upper tier radios, and they're in the $4,000 range starting point and go up from there. I've seen some of these, some of the upper tier pushing $10,000, which is about what I paid for my first house. So I have a little trouble with that. But they do have some pretty sophisticated radios, and they are once you get comfortable with operating, say on your entry level rig, there are some nice features when you make that step up to what I consider the upper tier. And then there's another level, and this is my terminology. I call it the exotic level. Elecraft and Flex Radio are two, and there's probably others, but these are the ones I've seen the most. I know people that have some of these, and they go from 5,000 on up to, kind of the sky's the limit. Well, I wouldn't say that, but you could easily say with an Elecraft or Flex Radio, or even these radios here, if you were to tie in a 1500 watt amplifier, you're going to be pushing anywhere from $12,000 to $15,000 to get that kind of a rig. In my opinion, this is for the fanatics. I'm not interested in these because I'm too cheap. Now, my wife might be, because she's a real ham nut. Another comment on the upper tier level radios for these manufacturers is that the Vhf UHF handhelds and the base units can be in the $650 range. And what that gets you over this entry level Vhf UHF is that there'll be more capabilities, there'll be more features in the radio. For example, these handhelds and base units, in addition to just normal FM transmission, you'll be able to do probably one of the digital modes like D-Star, DMR, Jesus Fusion. They have APRS, which is a system tied into the GPS of the radio that can automatically locate your position to other hams, so they know where you're at. So that means that radio also has to have a GPS in it. So what happens is you get a pretty capable, a lot of capability in a radio like this, which is, you would expect that for that kind of price tag. But you can, and I don't believe I haven't seen, I didn't do any research, but I haven't noticed Elecraft or Flex Radio doing Vhf UHF. They might, I just haven't found it. So I hope that kind of gives you a feel for the transceiver market. We'll take a look at some transceivers specifics. Now, what you'll be looking at will be Vhf UHF transceivers, and the configuration are basically two types. You can have a handheld or an HT, or you can have a radio that can either be mobile or a base unit. You can use it either way. For example, I have two Kenwood Ts590sgs, I think they are. It's Vhf Uhf, and I use one for the base in our shack, and then the other one is in my wife's car. And the reason I did that is that way she would be familiar with the radio regardless whether she was using it in her car or she was using it in her shack. So they're interchangeable. One of the main things with a mobile base setup, particularly that's handy for mobile, is that they're configured. The packaging is that you have the radio here. You can kind of see it in the background. And then this is called the control head. And this is connected to the radio with a, like an Ethernet cable. So you could put the radio, for example, I have it under the passenger's seat in my wife's pickup truck, and then mount the control head that controls the radio up on the console so she can operate it from there. And then the way I have it configured on the base station is that the control head's just attached to the radio, so it's a single unit. So that's one of the big distinctions on the mobile base HF radios. And then there's a variety of different HF transceivers. These are just some of them that I grabbed some pictures. Basically, most of them are intended to be base units in a shack. For example, I've got this one here. This is a Kenwood Ts590sg. And this started off as my entry-level HF radio. And then when my wife bought me a new radio for Christmas one year, actually I think she bought it for her, then this became portable, and I made it portable. It's a little big, but I just put it in a styrofoam suitcase and kind of cut the styrofoam so it could secure the radio. And then that is what we use for portable operations now when we go to state parks to do parks on the air. Or it did a fine job sitting on my desk in the base station. I think this is the ICOM 7300, probably the most popular entry-level radio now. And this is the Elenco here. You can see it doesn't have the color display or as large as the display, but it's configured so that it could be not only a base station, but it would be easy to install in a vehicle as a mobile radio. This is a Kenwood Ts-480sat. I have one of those. I bought that for mobile operation because it has the separate radio and the control head. I haven't installed it as a mobile operation yet. I've just had too many other things to do. So there's different configurations that you can get depending on what you want to do with them. And it's just some of the HF transceivers. Now, kind of looking, if you think back to that table for the market, we talked about import radios, and these are a couple typical. This is an HF transceiver. This is one that's pretty popular right now. I think it's around $600. It has a nice display. It gives you a frequency spectrum display or a band scope, which is nice to have. It is QRP, which means low power, has a maximum power of 10 watts, whereas the units we just looked at, most of them are at 100 watts max power. Here's another portable. I don't know if that's probably a Vhf Uhf radio. This is mobile. You could mount it in your car. And then this is a Bofang, forget what, UV5R, I think is the designation. And that's an extremely popular radio. It's the one you can get for about $30 on Amazon, and it has a rubber ducky antenna on it. I do have one of these that I use for when I go out on the pontoon boat, because I've got a couple nice Kenwood handhelds that are too pricey to risk on a boat. So I've just got a cheap, I call these Commie Radios. So I got one of these for the boat. And if it happens to go overboard, it's not that big of a deal. So Commie Radios do have their uses. But these, a lot of people use these, and that's all they use. If particularly the technicians, the people that are staying as a technician, or even if you get your general, you could still use this for your UHF, VHF work. So that's what some of the imports look like. And then this would be what I would call the, what did I call that? Kind of the higher level. This is a Kenwood Ts-890s. I think it's been out about 2 or 3 years. This is the one my wife bought me for Christmas, and it's an extremely fine radio, a lot of capabilities, very well done, and it is there. All the radios from those manufacturers I listed at this level are very, very consistent in terms of capabilities and performance in that. So there's really just a more or less minor distinctions from the radios, depending on how the manufacturer configured them. And then this is the mobile base unit I was telling you about. The one I have 2 of, and one in the car and one in the shack. And it has the detachable control head here, you can see, with the radio on the back. Like I said, in the base setup, I just keep it attached, and I separate them on the mobile installation in my wife's truck. And then this is a Kenwood Th94A, I think it is. And this is a pretty top end of the line handheld. It has the normal VHF, UHF capabilities, as well as D-Star. We'll get into that a little later, but that's a digital voice mode that can be used with the internet, that you can communicate around the world with the just the handheld. And it also has the APRS for positional information, and a GPS system built into it. And then just to show you an example, this was my first shack that I put together after I got my extra license. I think I got my extra license in, see, I have to think back, got my technician in general in March, and then I got my extra in June, and this is what I put together. I kind of like documenting what I had, so it's easy to know what you're doing. But essentially what it is I've got the HF radio here and a power supply, and we're going to talk about power supplies a little later. This is a VHF UHF radio with a power supply. I also have what's called an SDR, a software defined radio, and it with the computer, what that enables me to do is to generate the band scope with the frequency display on the computer, because this radio didn't have the band scope like the ICOM 7300 had. And that's worked extremely well. This is a Dvap D-Star dongle, and what this is, it's a UHF transmitter and receiver that plugs into your computer, and then you're able to use your handheld to communicate through the internet, through this dongle, through the internet, to other D-Star users around the world. As of this point in time, there are no D-Star repeaters within range. I think Phillipsburg has one, but it's fairly low powered, and it's not particularly well positioned for us to be able to hit it from here. So in order to use D-Star, I had to get this dongle. And now they've got a variety of dongles. Some of them can do all the digital modes, or you can get a dongle that'll do DMR or Yaesu Fusion, those types of things. And then I've got my antenna. This is my Vhf Uhf antenna, which at the time, I've since replaced this. It was just a mobile antenna. So that's kind of what how I got started anyway. Kind of shows you the components. And then another system I wanted to remind you of, we covered this I think in chapter 1 or 2, was how the Treasure Lake Sportsman's Club's ham radio group operates. And it is kind of the keystone of it is the repeater that we have. We'll get into repeaters a little later. And that enables anyone with a Vhf Uhf radio, any ham, to communicate with any other ham in our area that's also equipped. And we also have sold some receive-only handhelds to non-ham residents so they can hear what's going on in the event of an emergency. And then the link to the outside world is through the HF rigs that I think there's about 10 or 12 of us now that have this setup where we've got both the Vhf, Uhf radios for local communication, and then the HF radios that we can pretty well communicate anywhere we need to in the continental US. So that's how you configure a system with the different types of radios to meet your communications needs. Or at least that's how we did it. I'm sure there are other ways. Okay, now we're going to talk a little bit about data transmission. And this is kind of a general treatment of it. What we're looking at here could be a representation of maybe a local area network, maybe a network that ties into the internet, maybe a wide area network, but they all behave or perform in similar fashion. And the reason we're going to look at this is because this is the way that the ham radio communication systems work for different modes. So what you have in any sort of, say this is your computer at home, you're tied into the internet, which is here, and then you have a buddy who receives your email over here. So what happens, the sender will send a message or send data, and it'll go through what's called an encoder. And what it'll do is it'll take the data that's being sent and encode it in such a way that the other fellow knows what the encoding is so they can decode it. So it's this encode the signal, transmit it, the other guy receives it, he decodes it, and then that same information appears to his computer. Then it can go back and forth. So like I said, this could be just about any type of network, but the key is that both stations need to be on the same page in terms of encoding and decoding the information. Now, what you can do with amateur radio, even with a handheld, you can communicate with some repeaters that are tied to the internet, or they don't have to be tied to the internet. But if you can communicate with a repeater, the repeater can either send the information through the internet, and that's referred to as VoIP or Voice over Internet Protocol, and then the other station, the other repeater, will receive that information from the internet and then retransmit it, and somebody could pick it up here. So this is how D-Star, Fusion, DMR works, where it uses the internet to get the information. You can also use those modes without the internet if the repeaters are in a position that they could transmit that digital information through the air, and then you could go back to the receiver here. So the thing to keep in mind here is that what mode you use determines what hardware and software you need to use at each end. So you have to be compatible on both ends. The mode is the fundamental to understand here is the mode is how the signal is encoded and decoded. There's a lot of different ways to do that, but anytime you're using it, you're going to have to be on each end on using the same mode. Now there's some terminology we're going to go over here, talking about the difference between bit rate and baud rate. Now, bit rate is when you're sending data digitally, it's usually sent in a serial string where there's you're sending these characters down. You send 0, 1, 1, 1, 0, 1, 0, 1, 0, 0, and the bit rate is the number of characters needed, or the number of ones or zeros needed to designate a character. So there are some character sets that can be designated with only 3 digits. So the bit rate there would be 3. The baud rate, which is the number of characters, would be 1/3 of the bit rate. So say if you're transmitting this at 300 bits per second, and it's a 3-character or 3-digit character, then that means your character rate would be 100 characters per second or per minute or whatever the time unit is. So this is just so you don't get confused. People will talk about bit rate and baud rate. Then the thing to remember is that bit rate is the number of ones and zeros transmitted per second, and it doesn't have anything to do with the number of characters needed to represent, or number of digits needed to represent a character. But the baud rate is the number of symbols that are transmitted per second. So whatever your bit rate is, you can get your baud rate by dividing that by the number of characters of ones and zeros to designate a character. For example, I think ASCII has 5 characters, and that's one of the more common character sets that are transmitted. So this just explains the difference between bit rate and baud rate. We've already looked at this, but we'll just take another quick look. These pictures are probably a little bit better than the ones we looked at earlier, but this is the Amplitude Shift Key that we were talking about, where the signal is just transmitted when a 1 is wanting to be transmitted. This is the frequency shift key. You can see here is a lower frequency, and then here is a higher frequency indicating that we went from 0 to a 1, and then back to 0, and then back to a 1. Now the thing is, you don't have to worry about this because the software or the hardware that you're using is going to take care of this for you. But it just shows you the different ways that the signals are encoded. Here's phase shift key, and again, where the phase changes. You can kind of see the phase shift here a little bit better in this picture. And then there's differential phase shift keying, and I'm not even sure what that is. I've never used that, that I know of anyway. But there again, that's all determined by the mode that you select to use, either through the radio or through your computer. Now there's several digital modes that these digital modes will take voice signals, so from your handheld or your base radio, and convert the information, the voice information, to digital numbers. And what they're doing is they're all doing pretty much the same thing. This is D star, this is DMR, this is fusion. But essentially what they're doing is they're building a packet of data that's to be transmitted either through the electromagnetic waves from antenna to antenna or through the internet to another radio. But they have, each of them have a structure, and the structures are different. But generally, the packet of information is set up this way for D star, where you kind of have a header that passes along information with each packet, telling different things about the signal, and then the voice data is sent. The same thing with DMR. They talk about data here. They've got a data header that communicates, where it's coming from, where it's going, who's sending it, that kind of information. And then voice data in digital format. And then Fusion does the same thing. So they're all doing physically the same thing. It's just that the formatting of the packet structure is different between the modes. And I think that's one reason why we're seeing those dongle systems now that can operate any of these modes, either D-Star, DMR, or Fusion, or hard telling what else there might be bouncing around, because it's electrically it's the same. It's just the organization of the information that's different, and that can be handled by software. So they're just they're very similar. It's just that their data structure and the packets are different. Okay, now we're going to get into power supplies a little bit. There are two types of power supplies. The first one we're going to look at is referred to as a linear power supply. And what this is I'll kind of walk you through the schematic. This is an AC power source, probably 120 volts that you plug into your wall. And then that AC power source is connected to this configuration of components here. And this is what's called a bridge rectifier. And it has 4 diodes. And if you remember from the components discussion we had the last, I think it was chapter 4, a diode will conduct current in only one direction, and it'll block it in the reverse direction. So what happens is when this voltage source is positive, let's say, the current will flow here, and it'll flow through this diode, because that's the way the arrow's pointing, but this diode's going to block it. So this is like opening a switch. So we get a positive flow here to this capacitor, and then when it's negative, the current flow flows here, goes through this diode to the capacitor, and this diode blocks it. So this is like an open circuit. So instead of the sine wave that you have going from minus 170 to plus 170 peak voltage, you get this ripple, or not the ripple, but it's a pulse. Essentially what it does is it takes this bridge rectifier takes the negative part of this cycle, and instead of letting it go below 0, it has it go above 0 like this. Now if you were blocking it, if you were doing this with just one diode, what you would have, you'd have current flow here in this cycle, but then it'd be blocked, and then you wouldn't have any energy coming back in until this cycle. So this is a way of getting a direct current, direct voltage, half sine wave signal. Now what this capacitor is for is, if you remember, capacitors will store charge, so that as this voltage goes up, it's pumping charge into this capacitor, and the voltage will end up being at the peak voltage of that cycle coming in. And if there was no draw of current off of that capacitor, it would stay nice and steady. It would just stay at that peak voltage, because every cycle it would just come in and the voltage would already be at the peak voltage. But if you have a load attached to the capacitor, what happens then is that it'll be drawing current because there'll be a voltage across it, and that's what this is. And then as the load draws the current, the voltage is going to go down, and the greater the load is, the more current it's drawing, the farther down this discharge will be until the next cycle comes to recharge it. And you'll hear a term called ripple in power supplies, and that's what that is. It's the magnitude of this change due to the capacitor discharging through the load. And if you get too much ripple, you can actually drop the voltage, say below what the radio, if this load was a radio, below where the cutoff voltage is, and the radio won't operate properly. Ripple can also introduce noise into the radio, so the worse the ripple, the worse the noise. So this is just your basic linear power supply, and it's old design. It works well as long as you design your capacitor large enough that, depending upon the load, you don't generate more ripple than what you can stand. And that's all figured out in the engineering of a power supply. Now there's another power supply design called a switching power supply. And the difference here is you don't have as big of a capacitor as you had on the linear power supply, because the control mechanism here is a transistor that pumps current, switches on and off to maintain the voltage on the capacitor. So you don't have as the problem with the ripple that you have with the linear power supply. It's a little more, generally a little more expensive to build. It can have noise problems if you don't have a properly designed LC system here to filter out this pulse noise. But generally, this type of power supply will outperform the linear power supply in terms of stability and ripple and those types of things. The other negative with the linear power supply is that big capacitor in there that's holding the charge. They're typically an electrolytic capacitor that have probably the shortest lifespan of the components in a power supply. So it's not uncommon that a well-used linear power supply over the years will degrade, and you'll need to change those capacitors. But either way, it just depends on what you need for your particular application. But those are two basic power supply designs that you may encounter when you start shopping for them. I'm not going to go over this. I just included it. If you're interested, you can read it from the PDF file I send, but it talks about more detail on the operation and the differences between the linear power supply and the switching power supply. So if you want to get into it, there it is. And next, take a look at batteries. There's just tons of different kinds of batteries. I think the book went through discussion on the different types, the alkaline, the NiCad batteries. I don't know, the lead acid battery. That's used quite a bit on portable operations. We use a lead acid marine battery that's designed for trolling motors and those types of things to give us good power performance. We can probably operate. We have it's about a 70 amp hour battery. and we can operate with a lot of transmission time for about 10 hours or so with it. And the reason I mentioned the transmission time is that on a transceiver, it doesn't take that much current to listen, to receive. Where you really consume your power is when you're transmitting, because you may receive and it only take a few watts to operate the receiver in your radio. But when you're transmitting, say if you're transmitting at 100 watts, and just as a point of reference, let's say it's 50% efficient amplifier, you're using 200 watts of power every time the press to talk button's down. And there's another type of technology. I don't know if I don't see it in this list. Let's see. No, I don't. I forget what the name of it is, but it's a small. Bienio is one of the suppliers of the battery. It's a lithium phosphate, I think it is, and that's a new technology. You can get pretty good performance in a fairly small package, making it ideal for portable operations, or if you're backpacking, things like that. We have a small lithium phosphate battery for portable, and it's probably 10% the weight and size of the big battery, but I can get 3 hours of operation with high transmission rate out of that battery. So it's a nice little niche battery that's good for a backup. But the main thing is just when you're trying to figure out what batteries you just need to do your homework. And this was a good place to start. And that may be the last slide. Yes, it is. So I guess that's all I know about this, and hope it was helpful. If you have any questions, make sure you get a hold of me, and we'll see if we can get it figured out. So I'm ready to sign off here. This is K3SKS 73, and I'm clear. Thank you.